So I want to cover two facts that flow from the mean value theorem, which are also covered in this section of the textbook. I'm not going to prove these the formal way. I just want to give you some intuitive sense of why they're true. As usual, I'm going to put up a bunch of words. The words look scary. The picture is not scary. That's sort of generally the mantra for this chapter of the textbook is the formal description of what we're talking about. It looks like it's just this thing you could never possibly memorize or understand. Once I draw the picture usually is much easier to understand. So first one is if f prime of x equals 0 for all x in some open interval a b, then f prime of x equals c. In other words, f prime is just a constant function. Now, why is this true? Let's draw the picture. So I have here the interval a b, and I know that at every point in the interval, this function is just horizontal, right? Well, if that's true, then the only way that the function can just be perfectly horizontal. That's what the tangent line slope of 0 means. The only way it can be horizontal for every point in the interval is if the function is just a horizontal line. Now, I don't know whether it's that horizontal line or this horizontal line or this horizontal line, it's a little bit slanted, or this horizontal line, or maybe this one. It doesn't matter. That's why we're saying it just has to equal a constant for some constant. We don't know which constant it is, but that's true. The only functions that have a zero derivative for an entire interval are functions that are constant functions. Okay, or at least constant in that interval. It could be some piecewise function that's defined differently outside the interval, but the point is that in the interval it's just going to have the whole function has to be just a horizontal line. Now, um, in this case, number two, it's a related proposition, which is that if two functions have the same derivative for all x in an interval a b, then one of the functions, f of x, has to equal g of x plus a constant for some constant. In other words, the two functions have to differ from each other by a constant. So what that means is that if, let's say, this is a different color there, that means that if this is f of x, we'll do it backwards because that's the way they did it. If this is g of x, then that means that f of x looks like this. It might be this, or it might be this, or it might be this, or it might be this. We don't really know which one it is. What we know is it's the same function, just shifted up or down by some amount. A typical example of that would be that you can see this sort of easily, that if I do this, here's y equals x squared, here's y equals x squared plus 1, y equals x squared plus 2, y equals x squared plus 3. So think about this. If I say f of x equals x squared plus 3, its derivative is 2x, the same as it is for all these other parabolas. So all of these it's just the same parabola shifted up or down, and they all have the same derivative. What this is saying is that the only functions that have the same derivative as each other are functions that are just either shifted upward or downward. The proof of that is kind of like this. What we can say is that if I take this statement that f prime of x equals g prime of x, then that means that f prime of x minus g prime of x must equal 0. Well, we know that the function whose derivative is f prime minus g prime, because this is of course means that I have f minus g prime of x is equal to 0. What's the difference here? I'm instead of taking one function minus another, I'm forming a new function that is the function f minus g, and that function has a derivative of 0. We know from proposition 1 that any function whose derivative is 0 has to equal c, so that means that f minus g prime of x, f minus g of x, the original function, not its derivative, is equal to c. That means that f of x minus g of x is equal to c, and we have one more step. F of x equals g of x plus c. I'm just moving that minus g of x over to the other side of the equation, and that gives me the proposition that I want, which we kind of derive from the first proposition. So those are just two statements that you should realize are true, and we're going to make use of them in the next couple of problems.